complex mixtures composed of synthetic aroma chemicals, natural essential oils, and also fixatives dissolved in volatile solvent vehicle, typically ethanol. Due to the complexity of a single luxury fragrance, which can contain hundreds of volatile organic compounds ranging from light top notes to heavy base notes, the traditional wet chemistry techniques cannot effectively identify them. So, to overcome this analytical challenge, gas chromatography coupled with mass spectrometry or flame ionization detection serves as the industry gold standard for high resolution profiling. This technique separates volatile, thermally stable sand components within a capillary column based on its physical properties, yielding quantitative and also qualitative peak.
Now, let us look at the main chemical components found in perfume. Perfume contains essential oils and aromatic compounds such as alcohol, aldehyde, terpenes, and ester. Alcohol, such as linalool, give a lavender-like smell, while geraniol give a rose-like scent. Aldehyde, such as citral, give a lemon scent, while vanillin give a sweet vanilla smell. Benzoic acetate from ester give a jasmine fragrance. And lastly, limonene from terpenes give an orange or citrus smell. However, perfume also contains solvent, and the most common solvent is ethanol or alcohol. This alcohol helps the fragrance molecule to spread evenly when sprayed. It also evaporates quickly after the application. Besides that, perfume also contains fixatives that slow down the evaporation of fragrance compound so that the scent can last longer. And lastly, water is added to adjust the concentration of perfume. Now, now that you know this information, you might be wondering why a single perfume can smell like a combination of flowers, fruits, or other ingredients rather than just one scent. Alright, this is because perfume is made up of three layers of fragrance notes. The first layer is the top note. These are light scent that evaporates quickly, such as citrus and limonene. The second layer is the middle note, also known as the hard note. These form the main fragrance of the perfume. The common the common compound found in this layer is linalool, which give a floral smell. And the final layer is the base note. These are heavy molecules that evaporate most slowly and last the longest. The common example include musk compound and vanillin.
Hi everyone, today I'm going to explain the basic principle of separation in chromatography. But instead of using complicated chemicals, let's imagine we are separating the ingredients inside a perfume. Think of a perfume like a team of different fragrance molecules mixed together. Some smells are floral, some are fruity, and some are woody. Even though they are all mixed in one bottle, chromatography can separate them one by one. So, how does this happen? The separation depends on two important things: absorption and solubility. Absorption is basically how strongly a molecule likes to stick to a stationary phase. Imagine a stationary phase as a wall or paper covered with super sticky tape. Some perfume molecules are clingy and love sticking to the wall. Solubility, on the other hand, is how much the molecules like traveling with the mobile phase, like hopping into a moving bus. Now imagine this. If a perfume molecule sticks strongly to the wall, it says, "No thanks, I'm staying here." So it moves slowly. But if a molecule loves the moving bus more, it says, "Bye everyone, I'm leaving," and move faster. This difference causes the perfume components to separate. But why do some molecules stick while the others move away? The answer is polarity. Let's talk about polarity. For example, imagine our perfume contain molecule A and molecule B. Molecule A is more polar while molecule B is less polar. If we use silica in column chromatography as our stationary phase, which is polar, molecule A will love sticking to it. Molecule B, however, doesn't really care about the silica. It prefers traveling with the mobile phase, so it moved out first. Later, if we change the mobile phase to something more suitable for molecule A, it finally said, okay, fine, I'll move now. And that's how chromatography separates different perfume components, almost like sorting friends based on who likes staying home and who love going on a road trip. Now, why is retention factor? Retention factor or RF value is the ratio of distance traveled by the compound to the distance traveled by the solvent front. It is used to identify compounds and compare their polarity. Compounds with similar RF values under the same conditions are likely to be the same substance. The formula to calculate the RF value is distance traveled by the solute divided by the distance traveled by the solvent front. Both distances are measured in the same units starting from the original baseline. Let's say if the RF value is 0, it means that the compound did not move from the baseline and it has a strong affinity for the stationary phase. However, if the RF value is 1, it means that the compound traveled at this exact same speed as the solvent and it has a low affinity for the stationary phase. Factor affecting the retention factor, which are polarity compounds, amount of sample spotted, complex mixture, purity of solvent, and type of solvent.
Now let's take a closer look at results in gas chromatography. The final chromatogram results as shown in the graph display the separated components where each peak number represents a distinct compound. Using gas chromatography analytical methods, this technique is the highly important analysis tool for the perfume industry supply chain, as it allows aromatic compounds within the sample to be separated and identified. This method also helps perfume makers assess the effectiveness and quality of raw materials, ingredients, and final products. This gas chromatography chromatogram shows the separation of fragrance compounds present in Coco Chanel perfume. Each peak represents a different chemical compound detected at the instrument. The retention time indicates how long each compound takes to travel through the gas chromatography column, while the peak height shows the relative amount of the compound present. The large number of peaks indicates that the perfume contains a complex mixture of fragrance compounds. Each peak represents a different fragrance compound in the perfume, which in the early peaks, the graph shows light, volatile compounds like citrus and alcohol notes. In the middle of peaks, the graph shows floral compounds, but last but not least, the graph shows heavy, woody, or musky compounds. Perfumes can be analyzed through various effective initiatives, such as making a comparison between different perfumes. Different perfumes can be compared based on the number of peaks, peak patterns, and retention times shown in the chromatograms. Furthermore, the similarities and differences in the graph peaks can also be used to analyze a perfume product. If two perfumes show the peaks at similar retention times, they may contain similar fragrance compounds. Different peak patterns indicate differences in composition. Last but not least, calculating retention time refers to the time taken for the compound to travel through the gas chromatography column and reach the detector.
Focusing strictly on environmental sustainability, quality control, and structural identification. In the evaluation of water-based perfume analysis, Beckes et al. 2025 demonstrated that just 10 mg of solute and 10 mg of sample are needed for the PT micro-SPE method. That is PT micro-SPE, that stands for pipette tip microsolid phase extraction. Recent advancements in sample preparation have introduced PT micro-SPE as a technique that optimizes extraction efficiency while drastically minimizing organic solvent consumption. By directly adhering to the protocols of green inorganic chemistry, PT micro-SPE mitigates the environmental overhead of high throughput routine testing aligning analytical workflows with industrial sustainability mandates. Chromatography serves as a primary tool for quality control by establishing the precise chemical fingerprint of commercial fragrances. This analysis is mandatory to verify batch consistency and ensure strict compliance with international regulatory standards. Most critically, it allows for rapid detection and isolation of restricted allergens, synthetic impurities, and degradation products that jeopardize consumer safety. For precise characterization, gas chromatography coupled with mass spectrometry, designated as GCMS, is the industry standard for identifying and quantifying volatile fragrance components. This ordinary detection method provides simultaneous qualitative identification and absolute quantitative metrics. The resulting data enables manufacturers to generate accurate ingredient labeling that satisfies rigorous statutory disclosures. So, chromatography remains an indispensable analytical methodology. It provides definitive data required to enforce product standardization, consumer safety regulations, and environmental compliance across the global fragrance sector.